person here is a truly inspiring person on the MIT campus in a little bit of a different field, but it is no less revolutionary, the stuff that he's been doing in the energy field, revolutionizing energy storage. Professor Don Sadoway is here for many reasons, and he has a startup called Ambri that he's going to talk about, I think, hopefully, a little bit. But I wonder if we invited him because he also did some stuff on the MIT Gangnam Style team, which is very appropriate in this building. I don't know if you remember this video, the Gangnam Style, which is basically an area of Seoul. And I wonder how you want to start this off, with the Gangnam Style or with energy storage. Don Sadoway, here you are.
Well, thank you. I'm going to defer the Gangnam Style. That was pressure from the Korean Students Association. They pressured me multiple times, and I finally agreed to be in it. So I'm going to talk to you about a hardware-type company. This is stationary electricity storage. And, you know, electricity is tantamount to modernity. Everything that we value as 21st century technology is predicated on the availability of electricity. But you know, the electricity powering the lights in this room was generated just moments ago. Because the way the grid operates, supply has to be in balance with demand everywhere at all times. So what you're looking at is the world's largest supply chain with zero inventory. And we deal with this need to balance with redundancy and overcapacity, which leads to incredible inefficiency. And add to that the environmental imperative with the implementation of renewables such as wind and solar, but they're intermittent. So they can't by themselves be integrated into base load fully. So how do we deal with them? Their intermittency, redundancy, and overcapacity. Clearly storage is the missing piece. If we had storage, then utilities would have the ability to dispatch electricity on demand. And you know, the demand is so great, and yet it hasn't been met because the grid has uncommonly severe performance requirements. Super low cost, because it's not battery versus battery. It's battery versus fossil fuel. It's against diesel gensets, gas-fired peaking units. They're abundant, they're cheap. And the second thing is super long service lifetime. You know, storage would do to electricity what refrigeration did to our food supply. Imagine a food supply system without refrigeration. So with that as a background, when I started thinking about this about 10 years ago, first thing I did is disregard everything I know about batteries. Because everything I know about batteries is for batteries that fit in devices like this, and that's useless for grid-level storage. So I sought inspiration away from batteries. My other area of expertise, which is high-temperature electrometallurgy. And I looked at this. This is a modern aluminum smelter. Was invented in 1886 by a couple of 22-year-olds, Charles Martin Hall in the US and Paul Heroul. And with this technology, they took aluminum, which was a precious metal costing more than silver, and turned it into a common structural material. And I reasoned if I could figure out how to teach this thing not to just consume vast quantities of electricity, but to store them and deliver them on demand, I know at the end of the day it would be scalable and cheap, because we can make metal from dirt for less than 50 cents a pound in this reactor. So this is what I came up with. This is the liquid metal battery, and I'm not going to go into the details because the time is short. But basically, you're looking at what is, in essence, if I had to encapsulate this in a few words, it's essentially a bidirectional aluminum smelter. On discharge, it gives out current, and on charge, it takes current in. And it's simple. Liquid metal on top, molten salt in between, liquid metal on bottom. No membranes, no separators. The metal is insoluble in the salt, salt's insoluble in the metal. It's just like salad oil and vinegar, only instead of 2 layers, imagine 3 layers. So that was the basis of it. And round-trip efficiency is greater than 75%, which is better than pumped hydro. And yes, it operates at high temperature, and yes, allowing for the parasitic heat losses, 75% round-trip efficiency. All that's heartwarming, but this is the thing that makes this thing different. This is a cell that's been operating at a frightening high speed, 300 milliamp per centimeter squared, 93% depth of discharge. Full charge, 93% depth of discharge, you know, maximum stress test. And the fade rate is this number here, which, what does it mean? It means that if I were to discharge this thing every day for 10 years, I would retain 99.7% of its nameplate capacity. So that's the super long service lifetime, okay? And, you know, I have tenure. Tenure means never having to say you're sorry. And I don't care about publishing, but I want to launch the careers of young people who work with me. And this is an example of a paper that was published late 2014, ended up in Nature. And so there's some sound science behind this. It's not just cook and look. So in other words, to really do a good job in solving a major problem, you have to retreat to the fundamentals. And oddly enough, that's made it better. I, with two of my proteges, started a company. All the sexy names were already taken, so we came up with this boring name, the Liquid Metal Battery Corporation. And if you want a boring name, call me. I'll give you a boring name. And then we changed the name to Ambri. And the reason for Ambri, I got the inspiration from Cisco Systems. Cisco Systems was founded in San Francisco, and I invented this battery in Cambridge. So that's how we got the name. And then our Series A funding came from Bill Gates. Bill sought me. I'm from Canada. I'm very polite. Bill sought me out. Why? Because I wrote an op-ed piece in the Wall Street Journal? No, because I was teaching a big freshman chemistry class at MIT, which went onto the internet in 2004. And he started watching my chemistry lectures. And in August of 2009, I got an email from a woman who said she was his secretary and he was coming to Boston. He would like to meet with me for 90 minutes. Would I have time? Well, I disregarded the email. I thought the students had hacked into my account. So I disregarded it, and then she wrote again. Eventually I met him, and we chatted about distance learning and about computers and education. We talked about my chemistry lectures, and then we started talking about my research. And I had no results back then. I sketched this on a whiteboard, and at one point he says, you know, if you ever decide to spin this out, let me know. I'd be willing to put some money into it. And then he became our first investor. And, you know, it's a long road from the lab bench to the marketplace. I invented the cell chemistry, but then, you know, you got to invent the manufacturing facilities and the power electronics, the battery management system. So we established this. This is Phil Giudice, who is our charismatic CEO, and next to him holding the scissors is Governor Deval Patrick, who was governor of Massachusetts at the time. And we invented all the robotics and so on, how to build these batteries and whatnot. And this is what they look like. This is about 4-inch square. Each one of these cells has a capacity of 80 amp hours, which is, you know, way different from those little 18650 lithium ions. And then eventually we'll put 4 of these together, so it'll be 8 inches by 8 inches, which is 380 amp hours in a single cell. And just for reference, that's what a lithium ion cell looks like in comparison. Why is that important? Because if you wanted to make a 1 megawatt hour storage, you'd have to put 93,000 of those lithium ion cells together. If I gave them to you for free, who's going to wire those together? With ours, we could get away with 2,600, so there's a scalability factor there. So this is it. This is a 40-foot shipping container, or say a 53-foot trailer, silent, emissions-free, no moving parts, remotely controlled. It can act as a load as well as a source. And sometimes the way to balance the grid is not to call for current, it's to dump current. That's when you go to negative pricing. And it's designed at the price point of the electricity market. So I'm going to end with just some general things that I think I've learned from this experience. Everybody says, well, it has to be low temperature. And I said, no, I want high temperature because it's not going on your face, it's not going on your lap. So, you know, open your mind and ask the right question. Scaling, many, build a gigafactory. Gigafactory, it costs gigadollars. This, you get scaling by building fewer, but they're larger, all right? And then resources. I did this with students. And all of the students in my group, except for maybe one or two, had no background in electrochemistry, no background in batteries. I taught them to see the problem through my eyes, through my madness, and then we worked together. And so the notion that you get people that are steeped in the traditions of a big incumbent industry doesn't work for me. I'll tell you, you put me in a room, I present this, the strongest naysayers are from the battery industry, because they know that this is crazy, that this can't work. But my students are naive. They're young and ambitious, idealistic, and fearless. And so they make things. And global dissemination. Batteries in the United States should be built by Americans in the United States, not by Chinese in China shipped all over the world. Batteries in Africa, where 500 million people don't have access to electricity, batteries in Africa will be built in Africa by Africans using African resources. They become authors of their own future. So that's my vision of it. And I'll end by reminding you that it all started with a professor. The battery was invented by a professor, Alessandro Volta, at the University of Padua. And with his invention of the battery, which you can see here, the stack of coins separated by cardboard soaked in brine, he gave birth to a new field, electrochemistry, but immediately it migrated off into commerce. Within 10 years, there was electroplating and electroforming. But the other thing that Volta did was, for the first time, he demonstrated the utility of a professor. Until Volta, nobody imagined a professor could be of any use. But Volta proved if you give a professor resources and leave him alone, he's just liable to do something valuable. Thank you.